talk, I'd just like to briefly advertise that Stellenbosch, where I'm from, will be hosting the BRICS conference next year. So we hope very much that some of you will be able to attend that. We're hoping to be in person, but we'll see how that goes. Okay, yeah, some of the nice things you can do in the area. Okay, so yeah, to my talk, I was originally planning to talk about some recent work I've done with a couple of colleagues from the US on the ultraspherical spectral element method, but given that I don't have much time for this talk and the audience is quite general, I thought I'd spend, the time would be better spent maybe talking about the fundamental methods that underlie that new work, which is the ultraspherical spectral method, and indeed what are spectral methods. Maybe not many of you are familiar, so I thought I'd talk to you today about that. Okay, so part one will be what is a spectral method or an ultraspherical spectral method, and then if I have any time left at the end, I'll speak a little bit about the new work. Okay, so I'm a numerical analyst and I like solving differential equations. I particularly like solving not very complicated differential equations, but solving them very well. So what do I mean by that? Well, I'm paraphrasing my former PhD supervisor, Nick Trevethan here. We're aiming for 10-digit algorithms, which means we want roughly 10 digits of relative accuracy in the solution, and we want to happen instantly, in 1/10 of a second, and we don't want to write thousands of lines of code to do that. Plus or minus 10 lines of code should be enough. So as a toy example, I'm going to consider the area equation up here. It contains enough interesting things to get us going. So it's a second order boundary value problem, so we're not going to be able to use ODE45 or anything, any Runge-Kutta methods. We're going to look at these methods down here, which I'll discuss in a moment. The epsilon here is just to make it a little bit more interesting. It has these wiggles, and they get faster as epsilon decreases. And it's a non-constant coefficient problem, so that has a slight difficulty. So the solution is essentially given by this for this type problem. So there's no challenge really in solving this. It's just to demonstrate the methods that I want to be talking about. So everyone's probably familiar with finite difference and power series methods, and I'll discuss those briefly. And then I'll talk about Chebyshev methods, both Chebyshev collocation or pseudo-spectral methods, or Chebyshev series-based methods, which go by the name of Galerkin or Tau methods. And then I'll introduce the ultraspherical spectral method, which is a variation on those. Okay, so as I said, everyone's presumably familiar with finite difference formulas. So what's the idea? Well, you take your interval that you're interested in solving your boundary value problem on, you divide it up into subdivisions. And for convenience, we're just going to use equally spaced divisions here. And you approximate a derivative at any given point, so here uj, by the difference in the neighboring 2 points, essentially. Okay, and you can do the same thing for a second order derivative here, and of course there's some error involved in that approximation. And there are many ways of deriving these formulas, and one way of doing that is by polynomial interpolation. So this first one here we could get by interpolating uj minus 1 and uj plus 1 by a linear function and differentiating. That would give us this. And similarly here we could derive this formula for the second derivative by interpolating by a parabola and differentiating that twice, and we would get this formula here. But regardless of how you derive those formulas, you could then substitute those into your equation that you want to solve. And since this is a linear equation, that's going to end up giving us a linear system of equations to solve for the points on the grid. Sorry, it's Carl, I'm outside. Okay, so standard stuff. A lot of textbooks leave it in this form and say now you can go ahead and solve the system of differential equations. I think it's easier to think in terms of what I call differentiation matrices. So if we thought about the values that we had of the solution on each of these points and storing them in a vector u, we can think about the matrix D, which I've written here, and you can see how the coefficients correspond to those we had up here in our finite difference formula. So if I take those vector values and multiply them by D, I get, or maybe an approximation to the derivative values on the same grid. Right, so that's what I mean by a differentiation matrix. If I take the values I know, multiply by D, then I get an approximation to the derivative values. And similarly, we could get the second order differentiation matrix by using the second order finite difference formula here. Okay, and a multiplication matrix with x is just going to be the diagonal entries corresponding to the values of x. And then we can put all that together in a linear system. Looks like this for the equation that we wanted to solve. And then go ahead and solve this using standard software in order to obtain an approximation to the solution on the values of the grid. Okay, so standard stuff. What does that look like? And so we're going to see pictures like this for the different methods I want to consider. Over here is a sparsity plot of the linear system. And so that's this linear system here. Okay, so what does a sparsity plot? Well, it has an entry or dot here where there is a non-zero entry in the matrix, and if it's white, it means the matrix entries are zeros. So this is an example of a tridiagonal matrix, and tridiagonal matrices can be solved very quickly. There are specialized algorithms, but essentially you're just doing an LU factorization, and that's cheap because you're already essentially have a lower and upper triangular matrix. Okay, so in particular, if your matrix is n by n, you can solve such linear systems in n, what we call floating point operations, and that basically corresponds to time. So it will take linear time in order to solve these systems. Okay, the middle plot is just going to be a plot of the solution just because it looks pretty. Then the more interesting one over here is going to be the error over here as we increase our discretization size. So as we take smaller and smaller step sizes in our subdivisions, that's here. So n is the number of points we're taking in, and here is the error, I think just a pointwise error on the grid. Okay, so what do we see? Well, we see the error decreases at a rate 1 over n squared, which corresponds to the order h squared in our error, but eventually it increases because of conditioning and rounding error in these formulas, but I won't go into the details of that too much. But what we see, it converges very slowly, is what I want to point out. So we need 100,000 points to get 5 digits, and we can't get the 10 digits I'm aiming for in my 10-digit algorithm, so we're going to need to do something else. Okay, so what else could we do? Well, we could use a larger stencil. So here's a 5-point stencil. We're approximating now the second derivative by, well, we can think about interpolating these 4 points by a polynomial degree 4 and differentiating that, and that would get us this formula. Again, you can substitute that into your differential equation. You'd end up with a linear system to solve. What does it look like in this case? Well, the bandwidth of the matrix is increased, right? So it's no longer tridiagonal, it's a pentadiagonal matrix. That's still not too bad. We can still solve it in O of n floating point operations. The constant will be a little bit higher, but not too much. And what happens to the convergence? Well, since now our approximation to the second derivative was better, O of h to the 4, our convergence is better as we increase the number of points in our discretization, but we still have this divergence eventually because of the rounding error in the computations. Okay, so we still didn't manage to get to the 10 digits that I wanted, so we're going to have to do something else. You might think, well, I could keep increasing the stencil size, and eventually I would get there. But the problem you end up with is that, well, you can't do that. If you try and interpolate by a polynomial of larger and larger degree on uniformly spaced points, you end up encountering something called the Ringer phenomenon, where you get additional oscillations coming into the end of the interval. And that would become a problem here, and this divergence would happen sooner and sooner, and we would get no convergence at all. So we're going to do something else. It turns out you can continue with that idea if you're willing to move away from using uniformly spaced grids. So here we had equally spaced subdivisions. If we used grids which cluster near the end, and an example of that is what's called the Chebyshev grid, and you can think of those as being projections of uniformly spaced points on a circle. So if I had a semicircle here and I had uniformly spaced points around it and I projected them onto the real line, they would give me this exact clustering. So what we're going to do then is derive the Chebyshev collocation method, and the idea is really the same as finite difference method extended to this global interpolation. Well, imagine that we have the value of the solution at each of these points on this clustered grid. We'll interpolate by a polynomial, and since this is just a polynomial, we can differentiate it fairly readily and derive a differentiation matrix very similar to the way that we did for the finite difference matrix. The values in the matrix are a little bit more complicated, so I'm not showing them here, but it's fairly easy to compute those. Okay, so once you've done that, you can then go ahead and do the same thing as we did previously. You have a linear system of equations to solve for the values of the solution on the grid. You can go ahead and solve that using standard methods. Okay, you have to enforce the boundary conditions, and there are various ways of doing that, but I won't go into the details. So what does our picture look like in this case? Well, we end up with a dense matrix rather than a sparse matrix as we had previously. And why is that? Well, it's because we're using all of the nodes in order to derive our differentiation matrix. And as we saw with the finite difference, as we increase the number of points, our bandwidth increased. And here, well, because we're using all the points, our bandwidth fills the entire matrix. So we have a dense system of equations to solve, and that's going to take us O of n to the 3 floating point operation. So it's going to be more expensive to solve our linear system. So that's a price we've paid. What do we gain for doing that? Well, if we look at the convergence now, before we had a log-log plot, here we have a log linear plot, and we're getting a straight line. So that's indicative of geometric convergence. Okay, so we're getting convergence on the order of e to the negative rho n as we increase the number of points n in our grid. So in fact, rather than needing 100,000 points to get 5 digits, as we did for the finite difference methods, here we only need 50 or 60 points to get 10 digits. So although the matrix is dense, we can get away with using a much smaller linear system in order to solve it, and in the long run, we typically save computational effort. But what we'd like to do is try and improve on that. We'd like to try and end up with a sparse matrix with geometric convergence. So that's where we're going to consider some other methods. Okay, one other thing we might do is power series methods. We teach this to our undergraduates. The idea is that we take the solution to our differential equation that we're trying to find and expand it as a power series. we could then just differentiate term by term in order to find a power series for the derivative and the second derivative. And it's going to be convenient for me if I have x to the k appearing on the right-hand side. So I'm just going to, shuffle the indices as a standard thing, and we end up with these representations of the derivative and the second derivative. Okay, we could do the same thing for the multiplication operator, x times u. We'll just bring that in here, and again, we'll write it in terms of x to the k. And then very similar to as we did with the finite difference methods and so on, we'll take these expansions or approximations and substitute them into the equation that we want to solve. Okay, so if I do that, I take the second derivative here and this multiplication matrix we had here, you end up with this equality between the two power series. And then all we need to do really is equate coefficients. And you could think about that in terms of making the residual orthogonal and some suitably chosen in the product, but really you're just comparing the coefficients on the left-hand side and the right-hand side, because this has to be true for any value of x in the interval -1, 1. And so if you do that, you again end up with a linear system of equations to solve. The first one here sits outside because it's it's just the way it works out from the summation. But again, you can just write this down in matrix form, and we'll see that in a moment on the next slide. Okay, so that was the equation. We still need to do the boundary conditions, but of course you can get those just by plugging them in again to our expansion. If we plug in -1 here, we'd have -1 to the k appearing, so that's this, and that should be equal to 0. That was the boundary condition we chose in our toy problem, and similarly we can enforce a condition at the right-hand point. Okay, so again, we could write that in terms of differentiation matrices. Hopefully that's fairly evident, right? So this we could write down in this form, the second derivative here and the multiplication matrix, and we end up with a linear system. Since we, in principle, had an infinite number of terms in our power series approximation to the solution, this would be an infinite by infinite matrix, but in practice we would just truncate that to some finite length n and solve it using standard methods. Okay, so what does that look like if we apply it to our toy problem? We end up with a linear system that looks like this. So we had these two dense rows at the top, and they came from the boundary conditions. Let me just show you those again. Those were these. And then we have, again, a roughly tridiagonal matrix below. I'm going to call this an almost banded matrix. Right? So it's a banded matrix plus a small number of dense rows at the top. And it turns out you can, again, solve this very quickly in O of n floating point operations using the Woodbury matrix formula or a Shor complement factorization. That's fairly easy to do. And then what happens in terms of the convergence? Well, this is a little bit more interesting. So it turns out you get no convergence for quite a long time. You need to take n up to being roughly 70 or 80, I guess, here before anything happens. You then get geometric convergence, and that's nice, very much like we saw with the spectral collocation method just previously, but then your convergence plateaus about 10 to the -6 because of the ill conditioning of this matrix. So this approach has some nice properties. We ended up again with a sparse matrix, and we in some sense got geometric convergence, but it took a long time to get going, and we didn't converge down to the 10 digits that we were looking for. Okay, what happens if you look at the coefficients in the power series expansion? It turns out they do this. So here is, I guess I'm plotting k along this axis and the absolute value of the ukth coefficient in my power series, and it turns out that the magnitude of those increases for some time before it eventually starts decreasing exponentially. So you get this transient growth in the coefficients, and that's typical of these power series methods, which often do this, and then often also just will not converge for more complicated problems than the one we were considering. So we're going to need something else. So again, Chebyshev is our friend. I'm a big fan of Chebyshev. So instead of approximating our solution or expanding our solution as a power series, we're going to expand it as a Chebyshev series. So these are now not the monomials that we had previously. They're these Chebyshev polynomials, and this is possibly my favorite result in the whole of mathematics. This thing here is in fact a polynomial. It's very easy to show. We get our second years to do it in the differential equations course. But it turns out that expanding a function on a finite interval by Chebyshev polynomials is a much better thing to do than the monomials that we saw previously, but I won't go too much into the theory of why. Okay, so how does that work? How do we get our differentiation matrices and then the spectrum method that we want to solve? Well, again, we're going to substitute this expansion into our differential equation, so we need to know how to differentiate each of these terms. And again, they're just polynomials, so you can do that. The form is a little bit more messy though than we had for the monomials previously, right? If we differentiate x to the k, we get k times x to the k minus 1. That's nice and simple. It turns out if you differentiate the nth Chebyshev polynomial, we get formulas that look like this. So here's an example. If I differentiate t5, that's written in terms of t4, t2, and t0. If I differentiated t10, it would be in terms of t9, t7, t5, and so on down to t1. So this is what we would call a long-term recurrence compared to the short-term recurrence that we saw previously for the monomial expansion. So that's going to have some negative consequences that we'll see in a moment, but that's fine. We have a formula for differentiating each of these terms, and you can do the same thing for the second derivative. I've just not put that on the slide for brevity. So you can take then these formulas and compute a differentiation matrix, right? So this would be the matrix if we had the coefficients of u in a vector here and then multiplied by this matrix, it would give me the Chebyshev coefficients for the derivative of u, and same thing here for the second derivative. Okay, we want to solve our area equation again, so we still need a multiplication operator, and again you can derive such a thing. I won't go into the details, but you get another matrix that looks like this. And again, we're going to plug each of these expansions into our differential equation, sort of schematically shown here, and we're going to equate coefficients, right? So now we don't have x to the k on both sides, but we have tk on both sides, where we can equate each of these in order to solve for the uk's that we're looking for. So if you, again, plug in the boundary conditions to make that uniquely solvable, you end up with a linear system that looks the same as before, but of course our d is a very different thing, and our x. Okay, so again, it's in principle an infinite dimensional linear system, but we're going to truncate. Okay, so what happens? Well, we end up here with now an almost upper triangular matrix. We might call it a generalized Heisenberg matrix. So in fact, this is going to be faster to solve than our fully dense spectral method that we saw previously. You could do that in n squared flops, but we still like to do better. And again, you get geometric convergence. I'm running a bit slow on time, so I'll jump then into the ultraspherical spectral method, which is a more recent development. And I just then want to explain how this works. So I don't know if this expression translates into the languages of the other BRICS countries, but can we have our cake and eat it? So can we have both things, the best of both worlds? What I'd like is a nice sparse, let's say almost banded matrix like we had for the power series method, but I'd like geometric convergence as we saw for the Chebyshev spectral methods. Can we get both of those things? And the answer is yes. And the trick is this observation, that if I differentiate the Chebyshev polynomial as I did previously for the Chebyshev series, and instead of writing it as a long series of Chebyshev polynomials Tn, I'm going to write it in terms of what's called the second kind Chebyshev polynomial, which we usually write as Un. The formula is almost as nice as the Tn's, but a little bit different. Then we again get back to a short-term recurrence, right? I can write down the derivative of Tn in just one of the Un minus ones. So our approach is then going to be very similar to before. We expand our solution as a series of Chebyshev polynomials. We get the nice convergence properties of Chebyshev polynomials. But instead of approximating the derivative as a sum of tk's, I'm going to approximate the derivative as a sum of uk's. Okay, and then we end up with a nice diagonal, or almost diagonal, differentiation matrix mapping from these two different Chebyshev polynomial bases. Okay, so then let's just quickly consider a first order problem to explain then how we would then go ahead and solve this. Now we would substitute those expansions into our differential equation again, this one here. But now if we want to compare coefficients, we have a bit of a problem. We have UK's on the left and TK's on the right. So we're comparing apples with oranges, which isn't going to work. So we need to do something. We can either convert the UK's back into TK's, but then we'd be back in exactly the same Chebyshev polynomial method that we saw previously. So instead, the right thing to do is to turn the TK's into UK's on both sides, and then we could compare coefficients again. Okay, and it turns out we can do that. There's a nice sparse conversion relationship between those as given here, and we end again with a nice sparse banded matrix that we can do that. So those are the ingredients we need. We could then plug that into our differential equation. We now have apples on the left-hand side, so UK's, apples on the right-hand sides, so we can compare the coefficients, and again we end up with a linear system of equations to solve. Okay, you can do the same thing for the second order problem, like our toy problem. The difference is now instead of those Chebyshev points of the second kind, polynomials of the second kind over here, we have what are called the ultraspherical or Gegenbauer polynomials. But again, they don't have a nice closed formula like we do for the Chebyshev polynomials, but they're very easy to work with. They have lots of very nice properties. And we have this nice, again, short-term recurrence between the second derivative of the t's and these ultraspherical polynomials here. Okay, so I'm running out of time, so I'll go quickly. We end up with a nice differentiation matrix. We can, again, get a conversion operator between those two spaces, and then we end up with a linear system of equations that looks like this. So what does that look like? Well, we end up getting a almost banded matrix. So it's not tridiagonal anymore. It's a, I guess, septadiagonal matrix, almost banded. But again, we can solve this very quickly in O of n floating point operations, and we get the fast geometric convergence that we want down to at least the 10 digits. I'll briefly say that these ideas can be extended, so you can apply the same ideas for 2D problems just by taking bivariate Chebyshev expansions. It's been applied to singular integral equations. We've done some work in fractional derivatives and convolution equations. And what I was going to talk to you was about a spectral element method based on these ideas, but of course I don't have time. So I think I am out of time, so I will wrap up. And once more advertise that we are hosting BRICS next year, and it would be great to see any of you there in Stellenbosch. Thanks for your time.
For a very interesting talk on for a very interesting talk on the spherical methods and some other methods for learning models in release.
Pleasure.
Yeah. I want to know what is the progress of the work in higher dimensions, space dimensions?
So could you just repeat the question? It's not coming very clear.
If you have higher space dimensions, how easy or difficult it will be?
Yeah, so that's I guess what I skipped here. In regular geometries, so I'm sorry, let me go through it. In something like a square, that's not too difficult to do. You just do a bivariate Chebyshev expansion, and most of the ideas still apply. If you want to do something in more complicated geometries, like this, well, you have to do this spectral element kind of idea, which means to break it up into, let me show this picture, smaller pieces with some kind of meshing, and then on each of these small patches, we're essentially applying the 2D version of this method there and patching them all together in just the right way. Were you asking about dimensions higher than 2?
Yeah, it was I think she was asking this only higher dimension, but I will
Yeah. Okay. So again, on hypercubes and things, you could do that by taking I guess a trivariate expansion in terms of these Chebyshev polynomials. And there have been some, again, there's the references here, but there have been some references on other geometry, so triangles, spheres, even circular arcs and things. So it can be done. But yeah, it's sort of limited to the geometries that you can apply on with spectral methods. That's one of the limitations, but that's what we were trying to overcome by looking at this spectral element method based on these ideas.
Thank you for the talk.
Thank you.
So I have two questions. One is, what is the range of values of this epsilon?
So the range of values of
Epsilon.
Sorry, I still don't quite hear you clearly.
You
I'm sorry, I can't. I'm sorry, I can't. It's a little echo.
Okay, so now is it audible? Okay, so you have a parameter epsilon in the differential equation. So what is the range of values of this parameter in your computations?
Oh, you mean the epsilon that I had in my toy problem?
Yeah.
I was taking it. Here I took it to be 0.001. So it's not particularly interesting in this problem. It's essentially just you could do a change of variables, and all it's really doing is changing the width of the interval in this area equation. You can see that here in the solution.
So if epsilon is going to be very small, then your problem has a different asymptotic behavior where epsilon goes to 0. It's like a single neighborhood problem. So how does this spectral method take care of this behavior? Because asymptotically your solution is converting to something which is where the second derivative term actually disappears.
Yeah, I would think what would happen would be this geometric rate of convergence that you would get here. You would still get geometric convergence, but as you decreased epsilon, the slope here would decrease. So the rate of this geometric convergence is related to the annulus, the ellipse of analyticity around the interval that you're solving the equation over. And as you decrease epsilon, then what's happening really is that there are singularities in the complex plane coming closer to the real axis, decreasing the size of that ellipse, and therefore decreasing the rate of the geometric convergence. I don't know if that answers your question.
So, in this case, your mesh size is independent of epsilon?
Well, with the coefficients, there's not really a mesh. I'd have to. I haven't really experimented to see how the order of convergence decreases with epsilon. As I said, I'm not really particularly interested in this particular problem. It was just a demonstration for the methods here. But it would be interesting to see the, how does the convergence rate depend explicitly on that parameter? Yes.
Probably it has an effect because your electricity coefficient is epsilon, and that is going to 0.
Yeah, so as it's going to 0, I guess the solution is becoming highly oscillatory, and there may be a more specific methods that would be better for highly oscillatory problems. But this would still do a fairly good job, I think, for a generic method.
Okay, thank you very much.
Thank you.
Any other questions from online participants who have joined our Zoom? Okay, if there are no further questions, let us thank Nick for a very interesting talk.
Thank you.
Thank you.